only through the observation of our planet from outside, we can get a global picture of what is happening. Young generations means young ideas, and young ideas means looking further into the future of mankind. We are here in the main control room of the European Space Operations Center. This is the heart of the control center where most of the European missions of the European Space Agency are controlled. In this room, which as you can see is empty today, we don't follow the missions throughout their own life, the entire life, but we follow the critical phases of the missions. From the launch, where at the beginning of the mission more critical activities have to take place, and the more critical activities have to be followed by many people. And also in some specific moments, like the arrival at a planet, for example, of the flyby of an asteroid. The room is occupied by a maximum of 20 people, but normally less people are needed, depending on the phase of the mission and depending on the activities. Today we will make a tour of this facility. We will go more in detail in the roles of the people that work in this room, and also of the missions that are controlled by these people, and making with those sort of past, present, and also future history of the European space. The main control room in ESOC is used from a few hours before launch, which is the start of the mission. The mission starts in another location, of course, where the rocket starts, maybe in Guyana, in French Guyana in the South America, or it can be in Russia or in other places in the world. The people gather here, the controllers, the mission controllers gather here from a few hours before launch, and then when the spacecraft separates from the launcher at the end of the launcher ride, they take over control of the spacecraft. The people that occupy this room are located in very specific locations depending on their roles. And what you see in this first row is the location of the spacecraft controllers team. Sometimes it's called the flight operations team. It's a team of 5 to 6 people and led by the spacecraft operations manager, who sits normally in this position. The roles are in fact indicated by these signs, and the spacecraft operations manager is called SOM. Each person has 3 screens, 1 keyboard, and various tools here for the control of the spacecraft. On these screens, the information that comes from the spacecraft arrives and it can be displayed, and one of the persons in this team, depending on the mission, in this case would be the spacecraft controller that you see in that location there, is the only one who is authorized to even send commands, which is instructions to the spacecraft to be executed. People communicate with each other through headsets, and they can talk to anybody in this room, but also, of course, to other rooms and also other locations in the world, like the ground stations where we have antennae located all around the globe to communicate via radio signal to the spacecraft. And this panel here is also used to select the communication lines. We used to have phones. There are a few phones, but we use them less and less because the communications take place mainly over internet. In the back part of the room, we call it the back rows, the other controllers are located. On this part, it's the team that deals with what we call the ground segment, which is all the tools and equipment which is located on the ground that is necessary to control the spacecraft. So the network of ground stations, the antenna that communicate with the spacecraft, the computers that are located in this center, and of course the software that runs on it. The people in charge of that part of the operations are led by the OM, which is the Ground Operations Manager, and they have other support people in other rooms, but basically from here are responsible that all the activities on the ground part of the system work properly in order to be able to perform the critical operations with the spacecraft. In that corner, in fact, one very important role is the SOFCORD role. The SOFCORD is short for Software Coordinator, because all these computers have a huge amount of special software that was developed in particular for the mission, and this software has to run properly during the critical activities, and therefore there is a dedicated team led by the SOFCORD that takes care of the software that runs on the computers. All the activities conducted during the critical operations are led by one person, who is the Flight Operations Director, or FOD, who sits in this position of the room. There are basically three teams that are coordinated by the Flight Operations Director. The Spacecraft Operations team that we've seen in the first row of the room, the Ground Operations team that is on the back row on the left-hand side, and the third team is not located in this room, is the Flight Dynamics team. They're located in a separate room. All these are led by a single person, the respective manager, and all these respective managers report to the Flight Operations Director. The Flight Operations Director has the main decisional role in all the operations. He is the main authority to decide how to proceed in normal, but also in contingency situations where unexpected failures or unexpected situations occur, and a decision has to be taken quickly in order to proceed with the activities of the mission. And all the teams report to him and or to her, and the Flight Operations Director eventually decides. One normal situation in which the flight director has to take the final decision is what we call a go-no-go decision. There are specific moments in the timeline of activities which are set many weeks and months before launch that require a decision on to continue or not with the activities. For example, the go-no-go for launch. At the moment, just 10 minutes before launch, the launcher authorities, who are located near the launcher somewhere else in the world, ask the ground segment whether the ground segment is ready for launch, whether the ground segment is go for launch. This is the terminology we use. So the flight director asks all the people reporting to him to give a go-no-go. Each person will require to look at the specific area of responsibility of its role and give a go to the flight director. So the flight director receives a go from each responsible position, and then eventually the flight director decides, puts together all this situation, and then gives a go to the launcher authority, and then the launch can take place. But there are also anomalous situations where maybe a problem has occurred, whether it's a true failure on board the spacecraft or maybe a simply unexpected situation. And that's where the flight director has to take a decision. One example is the spacecraft did not manage to acquire its attitude, which is the pointing. Spacecraft has to acquire autonomously pointing of the solar panels to the sun, or maybe the pointing of the antenna to the Earth, in order to ensure the communications. And if this doesn't happen because of an onboard failure, because of a software problem, because of anything that was unexpected, the various experts of the satellite have to analyze the situation using the data that are received from the spacecraft, what we call the telemetry data, and then they have to identify what the problem was and propose ways to get out of the problem, to resolve it, and go back to the nominal operations. This process is led by the flight director. The flight director receives all this information, receives the proposals on what activities to perform in order to resolve the problem, and then takes the final decision in which direction to go. From the final decision of the flight director, then the various responsible have to take the necessary actions to resolve the problem. Resolving a problem like the attitude control maybe sometimes simply requires restarting a computer on board, or switching off a sensor that is not working and switching on a redundant sensor on board, for example a star tracker, a sensor that looks at the stars. And there are many situations, but since the system is so complicated, then the decision process has to be led by an experienced person who maybe doesn't know the details of the problem, but knows how to lead the decision process. How does this room communicate with the spacecraft? How does the room receive information from the spacecraft, and how does the room send information to the spacecraft on the activities to perform? All is done via radio signals, and the radio signals are not transmitted directly from this room, but they go over communication lines to the ground stations, what we call the ground stations, which are huge antennae, which are all around in the globe. These antennae are very large, depending on the distance of the spacecraft. They can be 10-15 meter diameter when the spacecraft is close to Earth, or even 35 meter diameter, which are needed for deep space communications, which is when a spacecraft is flying in the solar system, and it's hundreds of millions of kilometers away. Through these antennae, we send radio signals to the spacecraft. We tell the spacecraft what to do. We send computer instructions to the spacecraft via radio signal. And the spacecraft sends to us an enormous amount of information, what we call the telemetry, which is individual indications of what is happening on board, with the units, with the scientific instruments, with the attitude, with the temperatures, with the power on board. All this information, which we call engineering information, comes down via radio signal and is processed by the computers and is displayed to the engineers sitting in this room. The radio signal is also used by the spacecraft to transmit the scientific data, which is the purpose why we fly spacecraft. So all the pictures that we take of the Earth or of the solar system, all the measurements of the scientific measurements that the instruments on board are collecting are transmitted via radio signals to the Earth, collected by the stations and then transmitted to this room via communication lines. Communications are getting more complicated depending on the distance. If you communicate via radio signal to a satellite which is flying around the Earth only at an altitude of, say, a few hundreds of kilometers, then the communication is immediate. The radio signal travels at a speed which is the speed of light, which is very fast, 300,000 kilometers per second. So in a fraction of a second, you reach the spacecraft, the radio signal reaches the spacecraft, and in a fraction of the second, the spacecraft can respond. But if you fly in deep space, if you fly to the planets, if you fly to a comet, and you are at a distance of hundreds of millions of kilometers, even light that travels so fast can take minutes or even hours to reach your spacecraft. So when you're talking to a spacecraft that is flying so far away, you have to take into account that your signal, so your message to the spacecraft and the message the spacecraft can send to you, will take a very long time. So you cannot communicate in real time. You have to prepare everything in advance, send these instructions, and then wait for the answer that may come maybe half an hour later, depending on the distance. And this implies a very different way of operating compared to operating a spacecraft that is near Earth. But this is also what this center, the European Space Operations Center, is specialized on. We do not only control missions near Earth, but also missions in deep space. And this is what makes this center rather unique in Europe. One of the historical missions that were operated from this room is the Rosetta mission. Rosetta is the first and up to now the only mission that went to make a rendezvous with the nucleus of a comet. Comet is a very, very peculiar object that flies in the solar system. There are millions of them. They fly very fast. They have a very high energy, and therefore, to get to the comet, you have to reach their velocity, and the trip can last very long. When we launched Rosetta in 2004, we knew the trip would last 10 years. 10 years during which the spacecraft flew around the sun 5 times and used the gravity of the planets to be accelerated, finally achieving the necessary velocity that allowed the spacecraft to rendezvous with the comet. There is a picture here of the spacecraft Rosetta and the nucleus of the comet that we reached in 2014, the comet 67P Churyumov-Gerasimenko. As you can see, the spacecraft did not only orbit around the comet, but also released a small vehicle called Philae to land on the surface of the comet. This happened on the 12th of November 2014, and that was the highlight of the mission. The Philae lander reached the surface of the comet, survived for three entire days, during which this room was occupied, of course, 24 hours a day to keep the contact with the spacecraft and keep the contact with the lander and downlink all the possible scientific data that the lander performed, collected on the surface of the comet. But the mission lasted much longer. After having delivered the lander to the surface, Rosetta stayed in orbit around the comet for 2 years, until the 30th of September 2016. And it could study the evolution of the nucleus of the comet while the comet was getting closer to the sun and while it then started to go away from the sun. Getting closer to the sun, the surface of the nucleus gets heated up, and the comet starts emitting gas and dust. And this could also, of course, give a lot of information about the structure of the nucleus. Comets are very ancient objects. They are thought to be the remnants of the beginning of the history of the solar system 4.6 billion years ago. And therefore it's very useful and very interesting scientifically to study them, because you can sort of do archaeology in deep space. You can look into what the material that eventually formed the planets and formed the sun, what the material was, because it was preserved over all this period without being changed by the gravity and the pressure that was caused by the formation of the planets. Rosetta was a 12 years mission eventually, a 10 years trip to the comet plus 2 years around the comet, and had a lot of highlights that were lived in this room. One that was probably the most emotional was the wake up after the 2 years hibernation, 2.5 years hibernation of the spacecraft. Hibernation is a term that we use in space technology to indicate that we have switched off most of the spacecraft, so we have switched off most of the units on board the spacecraft to preserve energy. And this we had to do when the spacecraft was flying very far away from the sun, and its solar panels could not collect enough energy to keep it active. We switched everything off. We lost the signal for 2.5 years, and then after 2.5 years, we had some timers on board that would reactivate automatically, like an alarm clock, that would reactivate the spacecraft. And we pointed on that day, which was the 20th of January 2014, all our antennae to the point in space where we thought Rosetta would be, and we waited. And we waited for almost 50 minutes until the expected signal arrived. And this was an extremely emotional moment where everybody in this room jumped around. We knew that after 2.5 years of hibernation, the spacecraft was still active, was still alive, everything was working fine, and the mission could continue. Another very emotional moment was, of course, the landing of Philae on the surface of the comet on the 12th of November 2014. That was the only landing on the surface of the comet ever done in the history of space flight, and these are the moments for which this room is built, to actually make history of the European space flight. The European Space Operations Center controls many missions of different types. At the moment we have over 20 satellites in flight. The three main families of missions that we are in charge of controlling are interplanetary missions, so missions that go in deep space and fly to planets or to the sun or to comets or to asteroids. Earth observation missions, which are missions that fly very close to the Earth, and their objective is to take pictures and measurements of our planet. And astronomy missions. Astronomy missions are practically space telescopes that observe the universe. And we have here on these panels, just as examples, some of these missions. As interplanetary, we have missions to Mars. The European Space Operations Center has controlled all the European missions to Mars, starting from Mars Express, which was the first European mission to another planet. And Mars Express was launched in 2003, but it's still alive today and is still operating in orbit around the red planet. What you see here is the next Mars mission called ExoMars Trace Gas Orbiter, or TGO, which was launched in 2016 and reached Mars in October 2016, and it's still flying in orbit around the red planet. These missions have different objectives, from the study of the surface of Mars to the study of the atmosphere and the cartography of the surface and the analysis of what could be traces of potential signs of life on the red planet. A representative of the astronomy missions that you see here is Cheops. That's a telescope that is actually pointed to other stars in order to study what we call the exoplanets, which is planets that orbit around a different star from the Sun. They don't belong to our solar system. They are very, very far away. And it's very difficult to see these planets. And in this case, in the case of Cheops, it studies already known planets, but to study better, to characterize better their atmosphere and their properties. We have other telescopes in flight that observe the universe. For example, the oldest mission that is controlled by the European Space Operations Center is called XMM Newton. It's a telescope that observes in the frequency band of X-rays, which is actually a radiation that comes from the stars, but that cannot be seen on Earth because it's absorbed by the atmosphere of the Earth. So in order to see what the stars are emitting in this frequency band, you have to go over the atmosphere. XMM is flying since December 1999, and it's still very healthy, and it's still going to operate for many years in the future if nothing goes wrong. But we have other telescopes like Gaia, which is making a map of the galaxy, of all the billions of stars, at least in the proximity of the Earth. And we also have past telescopes that are not flying anymore, like EXOSAT, also in X-ray. And we have also a very peculiar telescope, which is called Integral, was launched in 2002. And this telescope observes very high energetic frequencies like the gamma rays. All these give us a view of the universe that would not be possible from Earth, because all this special radiation cannot be seen on the surface of the Earth. The third family is what I call the Earth observation family. These are special satellites that fly very close to us, only a few hundred kilometers altitude, say typically 600 kilometers. They fly very fast around the Earth, They fly in an hour and a half. They cover the entire orbit. So they go all around the planet in 1.5 hours. One example is a Sentinel there. The Copernicus program is a joint program between the European Space Agency and the European Union. And it's a series of satellites that we call Sentinels that observe and measure our planet for very specific characteristics. The oceans, the land, the atmosphere. They have radars, they have radiometers, they have all sorts of special instruments that allows, all citizens in Europe to receive information about the planet. And one very important role is, of course, the study of the climate of our planet, of how the processes that influence the climate are going. But also there are many practical roles, like supporting rescue teams during a catastrophe, like a flooding or an earthquake, or also studying the evolution of the oceans. So these series of Earth observation satellites are delivering a huge amount of data daily to special centers that then make these data available not only to universities or to governments, but also to the individual citizens of the European Union. Space pushes the borders of technology even further. In order to fly in space, you have to develop always new systems and overcome new challenges. This is not only a technological endeavor or a scientific one, but also a societal endeavor. Space requires very strong and very intensive investments, not only in terms of money, but also in terms of capabilities, know-how, and that's why space requires many nations together to cooperate. International cooperation is something fundamental for making progress in space, especially now that the easy targets have already been achieved. The new targets are extremely challenging and ambitious. We want to expand our knowledge of the solar system, and therefore we want to go to places which have never been seen before, or to land on the moons of Jupiter, land on the moons of Saturn, reach the borders of the solar system. In order to perform missions like this, we need to put together all the inventive creativity and resources of the population on Earth. The challenges that also the evolution of the climate on our planet is giving to our society can also be tackled through space. Only through the observation of our planet from outside, we can get a global picture of what is happening to our climate, what we can do to avoid that we are actually making it even worse. We can use Earth observation spacecraft to provide the necessary data to guide us in the usage of the resources, in the sustainable usage of the resources of our planet. So that's also a very important societal role of space. And of course, pushing the knowledge of the science into the universe, pushing the borders of astronomy, of cosmology. This is only possible today through the cooperation of ground telescopes, but also space telescopes that can observe the universe in a different direction. Today we have just launched very recently missions like Euclid from the European Space Agency, or JWST, which is a joint endeavor, NASA and ESA. These missions have only recently started producing their information, and they are observing the universe at a distance that was never reached before. And observing the universe in the far distance means also observing it into the far past. And at the moment we are reaching almost the beginning of time, the beginning of the universe, just a few hundred millions of years after the Big Bang. These are the new borders of space, and it is certainly a challenge that can only be achieved through the cooperation of many entities. But it's also a challenge for the new generations. Young people are the future of our planet, and space is the future of the planet as well. And therefore, putting more and more young minds and young people and resources into the space technology, into the world of space that we actually make real in a room like this, is certainly the challenge of the future. Young generations means young ideas, and young ideas means looking further into the future of mankind.